How about problem of the day? Today's problem of the day, it says if 4 inches and 6 inches are the measures of two sides of a triangle. So we got a triangle with two sides that we know at 4 inches and 6 inches. We want to find the range of possible values for the third side. So again, we're starting with 4 and 6 inches, two sides. What we're going to try to do is figure out the range of possible values. Notice there's an S on that, more than one, for the third side. Actually, there are quite a few that will work. So let's take a look at this problem a little more up close and personal. First, I'm going to just draw two segments that could look like a triangle side. How about it? Let's make them even accurate. How about I'm going to put 4, I'm going to use centimeters here, all right? It says inches, but I'm going to use the centimeter ruler because I'd be out of room if I try to use the inches on this. They'd be rather long for my screen area. And let's make another one here somewhere along the line here of 6. So this kind of gives you an idea, a picture of what we're talking about. So there are two segments, or two sides. This one is 4 inches. It looks a little bit shorter. Well, it is. Not only does it look, it actually is. There we have 6 inches, all right? And the question is, if we could draw an imaginary line across through here, how long does that need to be? Well, let's see what it is right now. With it, even as it's measured here, it's a little bit more than 8, but I guarantee you, let's see if we got anything. No, we don't have anything stronger. Well, we might have a little bit here. Nope, Curious George only does inches. I'm sorry. Well, actually, well, it was too bad we didn't draw it in inches, I guess. But you can see what's going on here, that this is going to be definitely longer than 4 and longer than 6. But if we started pulling this thing up like a hinge, we can start pushing up, 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 up. Guess what's going to happen? These 4 and 6 inch pieces are going to stay the same, but this distance is going to start getting smaller. So this is what I mean. There's a lot of ways that we can figure out an answer here that'll work, all right? Now, what would happen if I were to keep opening? I'm going to play like my hands are the edge of the triangle. If I keep opening and opening and opening, I wish I could go any further. I could eventually become a straight line. And folks, when it becomes a straight line, I can't have a triangle anymore. So that tells me something right there. When will it become a straight line, or when will it become all in one nice collinear pile of points? Oh, wow. When it becomes 4 plus 6 gives me 10. So I can't quite get to 10 theoretically. And I certainly can't go any further than 10 because then I'm way out of whack, all right? So that's telling me something. 10 is an important point right there if this were to go to straight line. So I want to keep it under 10. So that's going to tell me this third side has to be somewhere less than 10. Because once again, we're going to think of flexibility here. Now I'm going to tell you, there's a thing called the triangle inequality. We're going to use this. We're going to implore it to help us out here, all right? The triangle inequality addresses this situation. And it basically says that if you add the two smaller sides of your triangle, and we're going to say in this case, these are the two smaller sides. Some of you are already out there, but what if they aren't? Good question, and this is why we watch Mathline, because we want to find out what do we do if we have another situation. So we're going to say these two, what if these are the smallest? That tells me that this third side I have can't quite get 10. It can get real close. It can get 9.99. We may not be able to see it there, but it's there. There's still a little bit of space, all right? So we're going to say X for our missing side, and we're going to say it has to be less than 10. Fact is, can't open it any wider, okay? So if we were to connect from this point to this point, it's going to be less than 10, but it could be very close. But remember what we said, that hinge starts coming together. Oh my goodness, look what's happening. They're getting closer and closer. Can y'all see? I know I am. And eventually they completely close up. So the question is, where do we go? By the way, that from here to here, I wish I could have, maybe I could. Oh, there we go. Kind of like a tip to tip, all right? Everybody see the pen? No, you can't. It's probably blending into the background, right? What we have going on there is the fact it gets smaller up to a certain point. Then it collapses just like it would collapse into a line segment here if we got open to a certain point, which would be the length of 10. So we've got to be careful on that. So we have a boundary underneath. You say, well, Ernie, what would happen? Well, when it comes together, I've still got about 2 inches left from the tip of this finger to the tip of this one, all right? Because remember, one was 4, one was 6. So all of a sudden they come together and no longer can you connect those tips of my fingers. So what happened? Where did it go there? We still have 2 inches left, all right? So that's the other side of the coin. You can only, if 6 becomes the longest side, 4 can't be the longest side because we've already got 6, right? But with 6 being the longest side, 2 and 4 become, when they collapse, okay? When it becomes 2 or even less than 2, we have a problem. So what we have to say is that x also needs to be greater than 2. And that's our range of values. It can be fractional, it can be decimal in between there. Can't quite get to 2, can't quite get to 10. But the triangle inequality says, here's the key, the sum of the 2 smallest, or the shortest, we'll say, and that would be our shortest, lengths of a triangle, the sum, that means we add them, right? We add the sum of the 2 smallest, they must be greater than the third side. Than the third side. And that's when you have your 2 smallest, So in this case, we've got a possibility we could go almost to 2, 4, and 6. But see what happens when we get 2, 4, and 6 as lengths. 2 plus 4 equals 6. We're out of the bracket. We want to make sure 2 plus 4 is greater than 6. All right? So hence, we can't make 2 plus 4 be greater than 6, right? Unless we up the 2 a little bit. All right? So the 2 has this range starting at 2.1 or maybe 2.01. Or, oh my goodness, we could really, so we just basically, that's why we say 2 less than x, but then x would also be less than 10. That's on the other end because guess what? 4, 6, 10 doesn't work either, okay? So you can't have those, but you could have 4, 6, and maybe 9.99999 because 4 plus 6 is still going to be greater than. So what we're basically saying, our smaller sides, a plus b, must always be greater than the longest side, which would be c. That's the story there. So once again, how do you get those lengths? Well, it looks to me like you subtract it to get the lower length. It looks like you're going to add to get the upper one, but just make sure you don't get to either one of those. It's a limit type thing. You get very close, very close, but you can't quite get there exactly. So there's your range of values, anything between 2 and 10, as long as you don't get there. Notice we don't have the equals to. And that, folks, kind of a crazy problem of the day to start off with, but a little geometry going your way, and also pretty practical out there because there's not always can you make just any 3 numbers fix a triangle for you. All right, they've got to be in a certain king, and the triangle inequality rules the roost on that. So there's a good problem of the day.